All right, folks, let's talk about the next topic here, 2.51 kernel density estimators. And we'll see this is kind of an intuitive idea for trying to come up with a probability distribution from your data in a non-parametric way. Okay, so let us suppose that observations are being drawn from some unknown probability density p of x that we're trying to estimate in some d-dimensional space, which we shall take to be Euclidean, and we wish to estimate the value of p of x. And let me just highlight estimate, right? We don't know what the value is, we're trying to estimate it. Now, from our earlier discussion of locality, let us consider some small region R containing x. So remember what he means by that is earlier we were talking about how when we want to estimate the probabilities, what we need to do is just look at the points within, nearby to a central point of interest, and that's where kind of the Euclidean nature of the space comes in. But you can use other types of space and other distance metrics as well. Okay, so the probability mass associated with this region is given by the integral over the region of the probability density. So here's essentially the picture is just this one, right? So here is x, and you're just going to try to estimate p of x by looking at this region R of points near x. Okay, so now he says, suppose we have collected a data set comprising n observations drawn from p of x. Now, because each data point has a probability p of falling within R, the total number k of points that lie inside R will be distributed according to the binomial distribution, which has this interesting form. But okay, so an easier way, the way I would think about this is just think of each one of those points one at a time, right? And it's going to be a coin toss. So it's going to be a coin toss with probability p that it's going to fall in the region, and of course 1 minus p that it doesn't. So, and that's the bit that's going to be useful in what we're going to discuss in a second. So using this is a formula earlier. See, the mean fraction of points falling inside this region is, so if k is the number of points, is the expected value of k over n is p. So that's just that coin toss, right? So another way of writing this is, you guys can see this. Okay, so the expected value of k is n times p, right? You toss a coin n times with probability p. This is the number of heads. Number of times your points are gonna fall inside the region. And then if you've forgotten this variance formula, again, just think of, first note, what is he taking the variance of? It's not k, but it's k over n. So let's just look at the variance of k. So the variance of k, all you have to remember is that the variance of a coin toss is p times 1 minus p. And now we have n independent coin tosses. So that's going to be n times p times 1 minus p. And now then the variance of k over n is going to be this expression divided by n squared, right? So it's going to be that n squared is equal to p times 1 minus p over n. Okay, so you don't have to, all you have to remember is the coin toss and the variance for the coin toss. Okay, so that's where that comes from. Let's just erase some of this so we have a little bit of room to discuss. Okay, so the mean fraction of points falling inside the region is this, p, as you would expect, and by our definition basically. And we see that the variance around this is p 1 minus p over n. So the idea is that this variance, as the number of points goes to infinity, is it gets very large. It's going to become very tight. The same way that if the expected number of tosses that are going to come up heads is going to become very closely tight around p as the number of tosses increases. So it's exactly a coin toss situation. So k is going to be approximately np as n is very large, when n is very large. If, however, we also assume that the region R is sufficiently small that the probability density is roughly constant over the region, so this should get you thinking this is kind of like a histogram basically, then we have p is approximately equal to, its value, which is constant, times the volume of the region. Right? And then we just put these two things together and we end up with p of x is k over n times v. And this should be exactly reminiscent to you of what we discussed in the last video about histograms. So this is just another way of writing this, is p of x times v is equal to k over n. And you might remember, like in the histogram case, this was called, this was called P of I. This was, sorry, this was, what was that? It was delta I, that was this thing, and the K and the N were the same. So it's exactly the same thing. We can apply this exact idea to the previous, one-dimensional, two-dimensional case we're considering for the histogram. Okay. So now we obtain our density, which is, so the density is going to be the number of points in the region V, so divided by, and then you divide by the total number of points and by the volume. Or the way I like to think about it is that the probability mass in that volume V is equal to the fraction of points that fall inside it. I think that's a bit more intuitive. Okay, note that the validity of this depends on two contradictory assumptions, namely that the region R be sufficiently small that the density is approximately constant over the region, and yet sufficiently large that the number K of points falling inside the region is sufficient for the binomial distribution to be sharply peaked. Yeah, so I see kind of what he's saying, because I guess what he means is, you want kind of, I guess, P to be, I'm not so sure about this. So I think if you have enough data points N, you're going to get a peak distribution. So it's going to be a question of having enough points so that the distribution of points inside your region becomes sharply peaked. So not too sure about this statement. So let's just move on. Okay, we can exploit the result 2.246. So this is kind of a cool thing that he does here. I think it's quite an interesting idea. So let's just write this again. Okay, so that's this. In two different ways. Either we can fix K and determine the value of V from the data. So the idea there is we're going to say we're going to see so N is just we're just given. We can't do anything about N. So we have K and V to play with. So he says, well, we're going to just at each location figure out how big a volume do I have to consider to get K data points. And so if K is fixed, then V will expand, and we will then say, well, the probability over that entire region is going to be K over B. So this gives rise to K nearest neighbors technique discussed shortly. Or we can fix V, so we're going to look at a fixed volume and determine K. So just going to move this volume around and see how many points are falling in it. So this is kind of the histogram thing, and what we're going to be discussing in this section. Determine K from the data, giving rise to the kernel approach. And it can be shown that both these approaches converge to the true probability density in the limit N goes to infinity, provided V shrinks suitably with N and K grows with N. Okay. All right. So, okay. So we begin by discussing the kernel method in detail, which is what we're doing in this section. And we'll take the region R to be a small hypercube centered on the point X, which we wish to determine the probability density. Okay. So in order to count the number of points, it's convenient to define the following function. So what is this function? Let's have a look at it. So U is going to have D coordinates, and it's going to be 1 if the absolute value of all of those coordinates is less than 1/2. So this particular function looks at, let's just draw out what it does. We'll just do it in 2 dimensions. So this is going to be U1, U2. This is our grid points. So this is, minus 1/2, minus 1, 1/2, 1, 0, and similarly, it'll look a bit rectangular, but that's all right. So that's, again, this is the minus 1, minus 1/2, 0, 1/2, 1. Okay. So what this thing is going to do, this function K, it's going to be 1 inside, so this is the origin, it's going to be 1 inside there, and 0 outside. And so you just, so this is kind of a length of 1, going from minus 1/2 to plus 1/2 in each direction. So it's essentially kind of an indicator whether U is inside that region. Okay, so this represents the unit cube centered on the origin. The function K of U is an example of a kernel function. In this context, it's called a partisan window. Okay. Now how are we going to use this? Well, we're going to give it the U that we're going to use. So we got this X, and we've got our data points, X of N over H. So H is going to be our kind of length, our sense of scale. And so what this is going to do is it's going to see, whether, let's say, if we consider whether the nth data point is within H of X in all the coordinates, whether it falls within a window of, plus minus H over 2. So the quantity will be 1 if the data point xn lies inside a cube of side h centered on x, and 0 otherwise. So what we have is, we can put, x is going to be sitting there, and then our xn over there might be it's going to be outside the cube, or inside there will be 1 when everything's been scaled by h. Okay, the total number and the total number of data points lying inside this cube will therefore be, so what we're doing is we've got x is fixed, and we're essentially just counting, right? We're just summing over each one of the data points, scoring 1 if it's within that cube, 0 otherwise. So now we substitute this expression into 2.246, so there it is. So remember, it's going to be 1 over n times h to the d, that's the volume that we're going to be using, and then this sum up here, that's k, that's the number of points that we're dealing with. So this is exactly this expression that we had above. Okay, so, and he says, where we have used v equals h to the d for the volume of the hypercube of side h in d dimensions. Using the symmetry of the function k of u, we can now reinterpret this equation not as a single cube, and it's actually not a single cube, it's a bunch of cubes, but as a sum over n cubes centered on the n data points x of n. Yeah, so essentially what he's saying is, and I think this is kind of the way I think of it as well, is if you want to figure out the probability at a point x, you just sum up the contributions from all the various points. So all these various points are going to give you a 1 or a 0 if they're sufficiently close, and then you just normalize it properly so that you get a probability distribution out of it. It actually even makes more sense, more intuitive sense. It's the same logical sense when we consider the Gaussian case in a second. So as it stands, the kernel density estimator will suffer from one of the same problems that the histogram method suffer from, namely the presence of artificial discontinuities, coming from the fact that we are using these kind of sharp boundaries. So why not soften the boundaries? And the natural idea is to smoothen this thing, and we use another kernel function, the Gaussian. So now what we do is now look at this. We're no longer, it's no longer a 0 or 1 case. It's kind of a smooth drop off, determined by h. H is now the standard deviation, but again it has the same role as this kind of a scale. And so the idea is, let's say we have some data points here, and we're interested in the probability here is x. So all we do is we just put a little Gaussian over each one of these points, and then we just add those contributions up. And so the resulting kernel density estimator will just be the sum of those appropriately scaled. Maybe it'll kind of look like that, something like that. So each one of these data points, I think that's the right intuition to think about it. Each one of the data points is kind of giving you a little local bump of probability, and you just add those up. Thus, our density model is obtained by placing a Gaussian over each data point and then adding up the contributions over the whole data set, and then dividing by n so the density is correctly normalized. And so let's have a look at what it looks like, and here it is. So again, the points were drawn from here. He hasn't shown the data points, but they're drawn from the distribution. Now here he's used kind of a very narrow Gaussian. You can see there's lots of little wiggles, maybe not capturing it super well. If you use about the right size, then you can see that, okay, it kind of seems to capture what's going on. If your standard deviation, your scale is too large, you kind of miss all the action in the probability distribution. So again, but exactly the same situation as with the histograms, because in effect, they are the same thing with just a different choice of kernel here. Okay, so the parameter h plays the role of a smoothing parameter, and there's a trade-off between sensitivity to noise at small h and over-smoothing. Okay, optimization of h is a problem in model complexity. We've already talked about it. We can choose any other kernel function subject to the condition that they're all positive. So these are like probability distributions, basically. That's the way we're treating them, which ensures that the resulting probability distribution is non-negative everywhere and integrates to 1. The class of density model is called the kernel density estimator or Parson estimator, if you care about these names. You'll hear you'll see these as KDEs. Parson you'll occasionally see. So just good to know, but nothing to be afraid of. So this is cool. It has great merit. There's no computation involved in the training phase because this simply requires storage of the training set, right? So when we're computing these probabilities, we just need to know what the training points are, and then we just compute the contribution from each, and that's our probability. But now imagine if you have, 1 billion data points, and you have, another billion you want to evaluate the probability of. Do you want to kind of keep, it's a billion times a billion kind of lookups, basically. So, so this is one of the greatest weaknesses, because the computational cost of evaluating density grows linearly with the size of the data set. So, yeah. But yeah, again, kind of a very simple, I think, intuitive notion of how to define these probabilities in a kind of a non-parametric way, using these kind of current kernel functions. Good. So I hope that was useful. I hope you learned something. And next time we'll talk about nearest neighbor methods. So hope to see you then. Bye.